Okay, so today we're very fortunate to have Jacques Carette from McMaster University, who will tell us about what he learned formalizing category theory in Agda. So please, Jacques, whenever you're ready.
Okay, so diving right in. Right, so I really want to emphasize the I part and what I learned here. Some of the things, many of the things that I'm going to show you were known. And if you dig hard enough into various papers, you'll find references. So if you want to see proper citations, I wrote a paper with Jason Hu, and you can find citations there to who discovered what. But if you look in textbooks, the things that I'm going to talk to you about, they are not in textbooks. It's those kind of aha moments where I think more people should know these things about category theory that I'm going to highlight here. When I was going through and learning, I sort of had this, I really didn't know this. I wish somebody would have told me this. And that's what I've tried to fill this talk with. It's an open source project. There's a link. We love to have other people than just me and others submit PRs, and we've had a good dozen people do so. It's wonderful. So really, this talk is going to be about the design space of category theory when formalized. And I'm going to try and talk about that. So at the start, so this is a piece of software, we have to make some decisions. So since the decision was to make a library for Agda, we're going to stick to Agda, and we're going to use dependent types because we would be fighting the system otherwise. And that doesn't make any sense. Right? I'm not going to try to convince Agda to do set theory. I'm just going to fight it. So I'm going to try and go with Markov type theory as much as I can and see how that works. So that's obvious. The first part where things really are different is that the equivalence relation on palms, arrows, is going to, for me, carry evidence. So in a lot of different formalizations of categories, equality of arrows is a proposition, and we don't care. Propositions don't carry evidence. There's no, the proofs, we don't care about them. Once you have them, you have them. Here, we're going to care. Different proofs are going to be different. And this is just a decision, and we'll see how it goes. Composition respects that. The other decision is that where our objects come from, where our harms come from, where our evidence come from, we're not going to a priori decide that they must come from the same place. So technically speaking, we use different universes in Agda. The Agda universes are a decent approximation to Grothendieck universes. They're not quite right, but you can think of it that way if that helps you. And we're just going to make that design choice, that those three don't have to be the same. Modern category theory is weak, so we don't have equality on objects. We don't have it at all. You can't say it. It's just not there. So that's going to force us to we can't be strict ever. We just can't. It's impossible. So we have to be weak. So if parts of category theory are not, then we'll have to find workarounds. And going along with the second bullet, like Homs, like frequently when you say Hom set, well, no, they're just Homs from some universe, and that's it. We do have an equivalence relation, but that's it. So this is setoid enriched, or E categories, and universes, and so-called proof relevance, meaning the equality is not prop. So design decisions are choices. They're neither right nor wrong. So that's should be understood. It may not be a good set of design decisions in that they might make your life really hard, or they might be good and make your life easy. These design decisions are fairly natural from the point of view of Martin-Löf type theory. And in part, Jason and I kind of wanted to study this particular set of design decisions to see where it would go. About 4.5, 5 years ago, when I started doing this, I actually thought that this set of design decisions would lead to a complete dead end. I would learn something, back up, and go somewhere else.
Excuse me? You
Yep.
guys, a quick question to elaborate. What does the twiddle equivalence mean in this talk of Hom?
It just means equivalence. It's an equivalence you don't know. It is an equivalence, you get to set it. I think it'll become clear on the next slide. But I can't see the chat in this, so if people have questions, please interrupt. So what this allows us to do is to see a bit more about what happens in category theory. When I say there's fewer assumptions, it's because I didn't assume that Hom is a set. I didn't assume that objects and Homs come from the same place. I didn't assume that things are small. None of these things are around. Let's see what happens. So, okay, so let's see what happens. This is some Agda levels. You can think of them as universes. So set O, or a level O, is kind of one universe. And I don't even say which one's bigger or smaller or anything. They're just three completely different universes. So the first line defines a type of objects. The second line says, given two objects A and B, you get a type of Hom for those objects. So we don't have this type of all Homs, we have local Homs. For any object, you get an identity function, you get composition, and then the next three lines are basically where, for any category, I get to define what equivalence of two Homs are. So given two F and G, you get a whole type's worth of evidence that they are equivalent. It must be an equivalence relation, and composition must respect that equivalence relation. But this is basically a local equality. You get to program your own equality. Different categories can have different notions of equality of their Homs. This is very convenient because it's actually done in category theory all the time. Right. So let's dive right in to stuff we notice. Is op involutive? So, we take the opposite of a category, category op. We'd really like that to just be category, because if it's not, things are broken. So, And here, when I say I have a category, I've actually given the data of a category. So I'll call that a presentation. And so op is really a function that takes a presentation of a category to another presentation. And if you call that function twice, you should get back the category you do. And if you do things naively, you don't. The answer is nope, op is not involutive. Well, that's just dumb, right? If like right away, you don't even have this theorem, you haven't gotten anywhere. Well, okay, you can make it so that those two categories are essentially the same, but they're not quite. They're up to a proof. And the proof is when you take the opposite of a category, you need to take the proof that composition is associative and flip it around. So fine, it's a equivalence relation, you do sim. You flip it around again, sim. Sim, sim, great. But that's not equal to the identity. It's provably the same as the identity. And so therefore, the equality that you get here is up to a proof. That's kind of a pain. Kind of like better than that. And to do that, there's a nice little trick, is you change the definition of a category to have two axioms for associativity. Left associative, like basically this symmetric version. What does that give you? It gives you that when you try to do op on a presentation, you take these two proofs and you swap them. And when you do op again, you swap them back. And ta-da! Now your equality is completely on the nose. Even though like we have proofs all over and we don't know what they are, yep, now we've recovered that op works on the nose. And this is, you know, a cheap little trick, but and it's not ours, but it works nicely. So yay for symbol shuffling. And of course, if you now have to provide more data, like a second proof for defining a category, this would be a pain. You don't. The ways to construct a category give you the second proof for free. It's just a trick, basically. So other things like monad and natural transformation need the same trick applied for them to end up on the nose, being involutive with respect to op. It's not so hard, but it's kind of amusing that somehow the asymmetry of the definitions show up. Because we're in a setting where things are so fine that this actually ends up mattering. Technically weirder one, if you look at a functor from the singleton category to some category C, so this you kind of want there to be kind of a, especially the opposite version, there should be only one of them. But if you look, okay, so if you transport composition of two identities over, normally you get the choice. You can use the left identity law or the right identity law instantiated at the identity. You don't care, except that that's two different proofs of the same thing, and they're not the same proof. And that's a problem because eventually you shouldn't have such a choice. It should be unique. And the solution is to say, oh, actually, we're kind of also missing a proof that the identity composed of the identity is the identity. And this is a symmetric version. and then that's the one you want. The reasoning I've just given you for adding this is weak. And there's probably a much better reason why this is needed, but I've yet to learn it. So if anybody knows why, and at the end, I think I'm going to give you some hints as to where this is likely to come from, but still, I don't have a good explanation. Right. However, a nifty thing, the category of categories exists in this setting. And this is where programming your own equality wins. So if you give me 3 universes, then the category of at those universes, you just fill in the fields. I don't have to go to by category. There it is. Yeah, yes, associator, uniter, and for respecting composition, that is horizontal composition of natural isomorphisms. But you know, all the stuff that you would have defined for natural isomorphisms and so on, yep, they come in, you plug them in, there you go. The levels, i.e. the universes at which this exists, is different. So in the very first line, you see this successor. This basically says, okay, if this is going to exist as a category, then it must be in a universe that can fit at least O and L and E, and then you go up one. So this is our system telling us, yeah, there's size issues here. Like the category of categories is really of a different size than the things you started with. But I did not have to go to by category. I think this is probably one of the more beautiful results of very early setoid enriched categories is you know, you don't have to bump up a level. Meaning, sorry, you don't have to go to by category. You don't have to go to 2 categories. This works. Sorry, I'm trying to go too fast, and I should think it through. Right. Yeah, good. I'm just looking down at my notes to make sure I haven't forgotten anything. Right. Here's another question. Very early in almost all textbooks on category theory, it talks about the underlying graph. Now the question is that really categorical as a notion? And so I've drawn 2 categories. One is contractible. It doesn't have 2 points. I just drew it that way, but it's equivalent to the one on the right. But of course, the 2 graphs, you're looking at it and go, well, those graphs are not the same. That's kind of a problem, right? If we believe in the principle of equivalence, a functor in the category of categories, shouldn't be able to tell apart 2 things that are equivalent. And yet, it looks like it does. So if you try to prove, is there an adjoint between the underlying graph, the underlying graph or underlying quiver functor, a forgetful functor, and a free path functor, or free categories, it fails miserably. But if you take advantage of the fact that we can program our equalities, there's kind of an escape hatch. So on the left of the first underlying functor, it's kind of got a bad name. You call it strict cats. What it really is is the category of categories, functors, and strict functor equality. The functors must be the same on the nose. So there is a functor from that to quivers, i.e. graphs, and a functor on the other side, which is the path category construction. And you'll remark that the path category construction is kind of interesting in that it mucks around with the levels. So paths, objects are the same, but actual paths contain objects. And so that ends up getting reflected. And similarly, equalities contain paths, which contain objects. And so the functors don't quite work at the same level either. But if you fix that up by basically saying, okay, I'm going to, make my universes grow, they're ordered, then yes, indeed, you can prove that they're adjoint. This is sort of finicky, but almost in a good way, where we notice that we were a little sloppy, or we didn't take care between strictness and non-strictness of some of the concepts. And our theorem prover then goes, no, just try again. You're telling me complete BS, work harder. And so this kind of tells me, like, maybe we should emphasize graphs, like the teaching of category theory and its relation to graphs should perhaps be done in a more subtle way, because if you do it a little too naively, you might mislead, and it's right, like we basically, you go against the principle of equivalence when you do this. So I certainly found it quite interesting, because in all the textbooks where I learned category theory, this was one of the basic results, and Carette let me program that up, and it didn't work, and I thought it was me, and it really wasn't. There was a real problem. Okay. Moving on to slightly more advanced, well, no, still interesting category theory. Let's take a look at adjoint functors. And we can define adjoint functors between two functors L and R between two completely arbitrary categories. So we have 6 levels in play here. And the definition is straightforward. And then we have, if we take our textbooks and say L is left adjoint to R, if we have this equivalence of functors, like the hum functor is the same as the other hum functor, or you can specialize it and basically say that each hum set is the same as the other hum sets on the other side. And you ask Agda, let's do this, and it tells you that doesn't even type check. The problem is on the left-hand side, the hum D bifunctor is at level, ends up at level, like producing something in the category of setoids at level L prime, E prime, and the one on the other side as in the category of setoids L, E. So they're not even the same category. So you can't ask, is there a natural transformation between the two of them? It doesn't type. If you try and go, well, are the underlying sets the same? Well, yes, you can prove that, but they are still at different levels. Like they're not, like the question is still weird because they belong to different universes. It's not that what's in them is actually different. It's just that you're asking a weird question. Right. So they're unrelated, which I've explained. Of course, you can fix it. You can create a lifting functor that usually takes parameters, and yep, everything works. But this is inelegant. It feels wrong. And if you use a bunch of definitions that are based on HOMs, then this lift starts appearing in a bunch of different places, and this grates a lot on my sense of elegance. It goes, yeah, there's gonna be a better way, and yay, the answer here is yes, absolutely there is. We know there's a bunch of different definitions of adjoint functors, and there's a unit-co-unit definition. I just split it out there for you to read if you so wish. And if you make all of that into Agda, there's no mention of universes or HOM sets or HOM setoids or any of these things. And it just goes through. Fully polymorphic in all the levels, there's no problem, it just and then you can show that it's actually equivalent to the previous definition that has the lifts in them. So because it doesn't involve HOM sets and universe levels, then you go, oh, well, at least in this setting, apparently the unit-co-unit definition of adjoints passes my elegance test as being the nicer one to use. And yay, we had a bunch of different definitions we could use, and one of them won. My takeaway, in some sense, and it's colored by other stuff, is that the original definition, looking at HOM sets, is really too based on sets. Like it's not false. It's just that it came up through a historical development of category theory where HOMs were sets. And once HOMs, we did in enriched category theory came along, like some of these definitions became not quite as good. And others kind of peak up as being better. At least with respect to the set of design choices that I gave. I'm not saying this is the definition. That would be, no, it's just this is the one that in this setting is elegant. I kind of, so for the computer scientists and the crowd, so because we're universe polymorphic, this is kind of like parametric polymorphism or natural in kind of thing. This is better. This always feels better when you don't have to fool around with your free type parameters. This is also where in a bunch of textbooks that worry about size and things, you end up seeing locally small and various other assumptions that they kind of say, oh, if you do this, then all the problems go away, which is true. But if instead you want to be able to work super easily with large categories, very large, and so on and so forth, then you prefer the polymorphic version. Right. Let's move on to another thing you notice, and amusingly, this also showed up in a nice talk this morning in Ljubljana, fibrations. So here we have two completely arbitrary categories again, and a functor between them, and it's defined to be a fibration, and most like Cartesian with Cartesian squares, I won't explain everything, but basically you should mostly recognize the definition of a fibration, except that there's this ISO that normally isn't there, because normally we want the universal arrow to end up exactly be equal to A. But this is wrong. We're asking for a strict equality in a setting where we can't compare objects for equality. The best thing we can do is ask for objects to be isomorphic. Luckily, at this point, we didn't have to invent any new category theory. We could go to the NLab page on fibration, scroll down a lot, and see street fibration, and go, haha, that's already been fixed for us. We are just going to use that definition instead. All the normal fibrations are strict, and we don't need the extra generality. But like the strict fibrations are fibrations. They just make some of these things trivial. That's okay. And so this definition just works. And it was kind of, Agda sort of forced us, because of our design decisions, to go and look at the slightly more general definition of fibration. Because, and as the NLab page really says quite clearly, the usual definition of fibration is too strict. If Agda had been old enough, this would have been discovered, much earlier. It's kind of fun to rediscover it, because the system sort of tells you, hey, here, this definition. Something weird's going on. Okay. All right. So a bunch of the things that I talked about previously were categorical flavor to them. And now I'm going to switch where the lessons, the things I've learned, are much more on the usability or engineering side. Like I'm going to spend some effort on the engineering side to make the user's life nicer. We know that equalizers and co-equalizers are dual, of course. The temptation is to go, oh, I'm going to define one of them, equalizer, and I'm going to define co-equalizer by duality. Perfect, can be done. Then a little bit down the road, you have some theorems to prove that involve co-equalizers. You ask Agda, what do you need me to prove? And it shows you all sorts of stuff to do with equalizers. And your brain goes, this is all backwards. And like, I'm not equalizing anything, I'm co-equalizing stuff. Like, you're not helping me with my job by showing me everything in the opposite category. That's not where I want to work. I've got some work to be done. Why are you getting in my way? It really does feel like now the system is getting in your way by using the wrong language for the task that you're trying to achieve. So we decided, it's like purely a usability decision, that we're going to define both equalizer and co-equalizer. And in this particular case, only one name changes, but in other definitions, conventions are different name change, and it improves usability. Of course, they really are duals. And so we insist that they really are duals, more symbol shuffling going on. So if you take a co-equalizer and you change it to an equalizer for the opposite category and then go back again, that should be exactly what you started with. And that's what the second last line says. You do that back and forth, and you get back exactly what you started with. And the last line says, yep, Agda believes you. All you've done is move symbols around, and you've done no computation of any sort. And so there's a whole lot of duals that are unfortunately copy-pasted and changed by a human being for usability reasons of the library, but where we made sure to be able to prove the back and forth theorem with REFL for every single one of them. And that's a sanity check to make sure, yep, okay, we haven't done anything silly here. They really are exactly the duals that we wanted. It's from an elegance point of view, this is unsatisfying. Right? I talked about elegance earlier, and we changed things to make it more elegant. And here, what we really want is, or what I think I want, is some kind of meta-programming where I could derive the definitions one from another, but that in the library, they would look like they were handwritten. And so that from a usability perspective, you get the win. And from a library maintainer point of view, you don't have to repeat yourself. But we don't quite have that yet. So keeping on with equalizers, if you hang around with a lot of people who do these systems, they will argue over whether you should use predicates or structures. So the is equalizer is a predicate on an arrow, which says are F and G two given arrows. Like is the arrow R an equalizer of F and G? And below I have the definition, what is an equalizer of two arrows of F and G? It is an arrow R such that that arrow is an equalizer, has the property of being an equalizer. And we see it as a mistake to choose between these two modes. And a lot of libraries, there's been a lot of discussion, should we do it this way or that way? And by the or, they really mean exclusive or. We've chosen and quite uniformly, where we have both the predicate and the structure. And we find that extremely useful. To don't make that unnecessary choice. Yeah, just don't. Moving along as far as engineering lessons, again, continuing with equalizer. So if you look in the source code, you will see that below the fields, and it's a little hard to see because screen real estate, but the definitions of unique prime and id equalize are actually lined up with the keyword field and not with the keywords that are fields. So the fields are data that you must provide to show that you have an instance as a predicate. But once you've done that, then you get for free a whole bunch of other equivalent, sometimes there's theorems, sometimes they're equivalent formulations, there's multiple different things. In the, strictly speaking, these are definitional extensions of the theory. So is equalizer is a parameterized theory with 4 things, and a conservative extension of the theory is a theory with more symbols in it, but where that holds in all models. Basically, you haven't changed the models at all. And definitional extensions are those where the only thing you've added are definitions. An example of a conservative non-definitional extension is where you add a relation between things, where that relation already held, you just didn't know it yet. Fine. We have a theoretical framework that helps us explain and understand why we add these things. Agda lets us, in an engineering sense, add them directly to the record. So it's very convenient because sometimes there's slight tweaks to the normal definition. I don't know if equal is, well, here, like there's two different ways people like to prove uniqueness. Instead of choosing, you just have both. And this just makes things more usable, which is convenient. The temptation is to put in a lot of these. One has to be careful. So I'll come back to that close to the end. But generally, if there's 5 or 6 convenience functions, just throw them in there. It helps the end user quite a lot. Good. Equational proofs. So again, so here is another conservative extension or a definitional extension of equalizer, that it respects equality. But at the bottom, you'll see that I wrote my proof in an equational style, which is basically I is actually the same thing as a morphism as H, which is the same thing as a morphism as to arrow composed with equalize EQ. And the reason for that is, well, one of the assumptions was that H is the same thing as I. And I flipped that assumption around. That's the little smiley face on top of the equal. And then the reason H is the same as below is that's exactly that H is universal from the axiom. I could have written that proof as trans sim H composed I universal. And Agda would have said, perfect. Humans would come along, and especially when the proofs are way, 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 way bigger, human beings would come along, look at those proofs, and go, that is completely unreadable. I have absolutely no idea what's going on, and would have to look at it very, very, very carefully to reconstruct what's going on. So here we can sort of read that proof by transitivity going down on the right-hand side of the explanation, but all the rest as annotations are for human beings. And I could have shown you much larger proofs. There are equational proofs over 100 steps long in the library. They're just absolutely enormous. But you can kind of follow along because it tells you where it's going. Of course, ultimately, most of these proofs are diagram chases. So even better would be to plunk a diagram here with the edges properly labeled and the various transformations. That would be absolutely fantastic. But we don't have that. Reconstructing the diagram from the equational proofs is easy. If you go in any system which is tactic-based, trying to figure out what the proof means and what diagram is actually hiding in your proof, good luck. It's really, really hard. So we should see this also as a usability help, so that you can actually go and read the sources and understand the proofs without any help. They're written for human beings to consume. Last sort of usability engineering lesson. There's a big issue on whether to bundle certain things together or unbundle them. And so here, the first line basically says, oh, I'm going to use a different version of category that is unbundled. And you can sort of guess that. And in the third line, I see that C is a category over a set of objects in 2 levels, where obj is given on the line above as some set. And here we can see that the category C and the category D share the same set of objects. They share it on the nose by declaring it so. And then we can define what it means to be identity on object as a functor. I don't quite say, we can make a functor out of this. And the transformation of C arrows to D arrows, which you can see on the F1 line, is interesting because it goes from A to B, like the endpoints are AB and AB. And the only reason this type checks is that the objects of both categories are the same, because normally you can't do that. Right? You have to take like your F0 map and map them over. But here we know, we baked in that it's going to be an identity on objects functor. And so we don't want to post facto say, oh, but that function was the identity. That leads to hell. It's awful to work with. It is horrible, horrible, horrible. It's much better. And I had some nice conversations with various people on the category theories who said, yes, it is much better to define this as a separate structure. And then, yeah, indeed, this induces a functor. And we can see that below, which is that functor, get all the right data, you get one of those identity objects thing, and out comes a functor on the packed version of C and a packed version of D, meaning the bundled versions of category. And Agda is even kind of nice. Like, of course, we want to say that the F0 is the identity. And then we take the module version of that record and say, put the rest here. And it does. Just all the rest of the data, it's here. And that's a satisfactory construction. So that's why is this surprising? Why is this? Because if you look at most of the literature, and if you work in a classical setting, the difference between having the F0 map be the identity by construction beforehand or being the identity after the fact really doesn't make any difference. But in the set of design decisions that we've made, it becomes awful. Like the two different ways of looking at it end up being quite different. Again, this is somewhere we would be nice to have some engineering help, because it's very tedious to write some of these things by hand. You feel like you cut and paste. Oh, okay. I went slower than I expected. I actually don't have that many slides. Anyways, lastly, well, a couple of things. Talk a bit more about levels, i.e. universes as a signal. And here, there's a whole lot of information on the screen or the formally correct definition of a comma object and a comma arrow to form a comma category. The only important line is the very, very last one. It says that from 2 functors that when you create a comma category, what are the levels? You're mixing the objects of category A and category B and the morphisms of category C into the objects of the target category. You're mixing the morphisms of A and B and the equality of C next. And you're mixing the two equalities of A and B, which is good in the end. And in fact, the interesting thing is you're never actually even mentioning any object of the category C that didn't come from somewhere else. So that level doesn't occur. What does that, like, this is not a problem. This is just correct. But it's a strong signal, an alert, that if you're working with categories of different sizes, the comma category, and thus slice and co-slice, you may have size problems. Things might not be quite the way you expect them. And this comes in because slice and co-slice categories occur a whole lot in models of type theory, especially dependent type theory. And once in a while, you're going to fool around with, small illumination and big illumination and this and that, and then boom, things won't work. I think a lot of the time, the reason things don't work is that last line. You're fooling around with sizes, and you didn't know, at least, of course, the real experts, they all know this. Not just, it's not new, but it's kind of neat how it sort of shows up. Your assistant kind of tells you, proof assistant kind of tells you, here is an issue, pay attention. This may cause you a headache down the road. Right. Enriched functors. So the first line is the definition of a normal functor between two categories with 6 levels. Next, we're going to have like set of categories, just our normal categories, but inside, when I look at record category and record functor below, those are supposed to be enriched categories. I should have called them enriched category and enriched functor, but it gets ugly. So yes, we have the data of a monoidal functor, a monoidal category V, over which we're enriched. When we do an enriched category, we get a new level. The objects come from somewhere completely unrelated to V. Unfortunately, it's called V, little v, that's a mistake. So you end up with 4 levels to an enriched category, which is a pattern that recurs. Every time you enrich, you get one more universe that you can be free in. And then you look at functor, okay, yeah, I've got a category, an enriched category over V with one more parameter, C, same over, and then the functor ends up depending on 4 universes. This is deeply weird, because why would enriched functors, which are really supposed to be a generalization of functors, depend on less? The reason is our original functor is actually setoid enriched, but we did it by hand so that a change of base between one setoid and a different setoid was baked into the definitions. And in the ones in textbooks for enriched functors, it's not there. So yeah.
Sorry to interrupt, but I see you're close to finishing your slides, but we're also running out of time here. So if you could move to wrap up in the next few minutes, thanks.
Yep, I will. Okay. So there's some observations. I can post the slides. I've got a couple of conjectures that I will really quick. Basically, if you fool around with negative thinking, it looks like the -1 categories, the category of -1 categories isn't really the same thing as 2 unless you have equivalent excluded middle. And my conjecture is that those two things are like the equivalence of those categories is equivalent to excluded middle holding. In one direction, I have the proof. In the other direction, I have been unable to finish the proof. It looks like it's there, but I just can't. And there's more, just as strange, the forgetful factor from cats to setoids normally wants, like cats to sets in the normal setting has a left adjoint, which is the discrete functor. And because we have a different setting here, that one doesn't want to work. Here, it's not a size issue, it's an equality issue. The equalities don't want to agree with each other, no matter how you tweak things. And I really think that this one, no, there isn't any in this setup. That theorem is a theorem about strict category theory, not weak category theory. All right, and last slide. The fact that there's a lot of huge category theory libraries and many different theorem provers, to me, is an indication that category theory is extremely robust with respect to change of foundations. And I explored one corner and it worked. And other corners very far away have been explored and it works just as well. And I think that's kind of interesting how robust the whole setup seems to be. You have to do tweaks, but it's robust. Some of the, like if you're an expert, some of the tweaks that I've had to do is basically there's stuff leaking in from bi-category theory, and other pieces of category theory are kind of slow, leaking in a little bit to setoid enriched category theory. And that's why some changes need to be done. But all mainly, wow, doing this is so much fun. It's just ludicrous. Done.
Thanks, Jacques. That's really interesting stuff. Fun to hear all the lessons that you've learned from doing this over the years. So maybe we can take one or two questions before we switch to the open discussion session. Yeah.
I have a question. I'm Owen. I'm off the screen from Evan. Oh, yeah, here. So you say that this is setoid enriched category theory, but it really seems like it's groupoid enriched category theory. Can you say a little bit about that?
Well, to a certain extent, it's zero groupoid enriched category theory. If you're really doing groupoids in this setting, then the groupoids themselves have equivalences that we don't have. It's a little hard to explain. But it's slightly different. Like I'd have to pull up a whole bunch of.
Sure. Well, okay. So you're saying that like groupoid would also include like equivalences between the arrows in the groupoid, and we don't have that.
There's more data in a groupoid than in a setoid.
Okay.
Okay, so maybe what I'll do is let's thank the speaker again. And so I stopped the live stream. So